to the Louis CCOM seminar. Today we have Thomas Blanford presenting to us. Thomas C. Blanford received the BS degree in electrical engineering from the University of Notre Dame, USA, in 2012, and the PhD degree in acoustics from the Pennsylvania State University State College in Pennsylvania. This was in 2009. From 2012 to 2017, he was an engineer with analog devices and InvenSense, where he developed low-power, high-performance microelectromechanical systems, MEMS, microphones. From 2019 to 2023, he was an assistant research professor with the Applied Research Laboratory, the Pennsylvania State University, with a faculty appointment in the graduate program in acoustics. He is currently a research assistant professor with the Center for Acoustics Research and Education and CCOM. His research interests include the design and modeling of sonar systems, acoustic navigation, and signal processing in acoustics. Welcome.
Thank you. Most of what I do is develop sensors using acoustics that work underwater. I kind of got into that early in my career working on microphones. We were making little tiny microphones out of silicon, putting them in hearing aids and cell phones. I ended up at Penn State University doing research there and ended up working in underwater acoustics like most of us do because I thought I'd be doing something else and just ended up doing it. And that's what I've been doing ever since. I've been at UNH for a little more than a year now. So if this stuff is interesting to you, I just sit upstairs, so stop by and let's chat. What we're going to talk about today, though, is working with coherence, or just the similarity of acoustic signals. And we're going to talk about how I'm using that in navigation underwater, in imaging underwater, and then how we're starting to use that for monitoring changes in the seabed. So when we talk about coherence or similarity, I think about it mathematically with the correlation coefficient. And it's my presentation, I picked the variable rho. I didn't make it really big on this slide because we're 4 slides in. I wasn't sure I'd remember what we're talking about anymore. Rho's great, right? The correlation coefficient, it's going to be between 1 and -1. If it's 1, the signals are the same. If it's -1, they're the same, just moving in opposite directions. It could be something in between. The acoustic signals I work with are generally complex valued in their representation, so it gets even easier. We're just going to worry about the absolute value of the correlation coefficient. And so it's between 0 and 1. If it's 0, the signals have nothing to do with each other. If they're 1, again, they're the same. So it's got this great property that it's bounded. We can work with it. We can see a correlation coefficient, understand how similar 2 signals are. It has some less desirable properties too. So its estimator is biased. If we try and measure the correlation between 2 signals, we're always going to get an answer that's actually a little bit higher than the 2 signals actually are correlated. If you're trying to do some math with it, its PDF is challenging. So sometimes we have to abandon it, and we need to use another measure of coherence. And for that, we look to covariance, and I like the variable gamma. It's got this great property that it's unbiased when the correlation coefficient is. The PDF, it can get messy, especially when it's complex valued, but it's workable. It does have an undesirable property in that it's unbounded because it's proportional to signal power. If the signals get louder, covariance goes up. So we can't really look at the magnitude of the covariance and learn anything about how similar the signals are, like we can with the correlation coefficient. All right, that's enough of the math. So we're going to talk about how to use this for navigation. This project was looking at a navigation aid or an acoustic sensor for small man-portable underwater vehicles. So when the platform's this small, you don't have a lot of room for a battery, so the sensor has to be really low power. You also don't have a lot of space to put your acoustic array, so you're working in a really tight footprint. And then these things are designed to be inexpensive. They're probably not coming back, so your acoustic sensor also cannot be that expensive. When you're navigating underwater, you don't have GPS, so generally what you do is you dead reckon with an inertial measurement unit, an accelerometer and a gyroscope. Those drift, and so you have to correct for that drift with some sort of ground referenced aid. Most people use a Doppler velocity log, and this gives you a measure of how fast your vehicle's moving relative to the seafloor. It transmits 4 narrow beams at grazing angles, and it gets velocity based on the Doppler shift in the returns. So for those of you who use ADCPs or acoustic Doppler current profilers, this is the same technology. Just instead of looking up into the water column, it's strapped to the bottom of the vehicle looking down. For these to be accurate, the beams have to be really narrow, just 1 or 2 degrees wide. So in a space-constrained platform, the only way to get those narrow beams is to run the operating frequency up really high, into the megahertz. Underwater, high frequencies get the most attenuation. So transmitting signals that are going to reflect off the bottom, come back to you, and actually be measurable at any range they want to operate these vehicles off the bottom, it's just not practical. They don't have enough power to do it. So an alternative approach is called a correlation velocity log, or a CVL. These work by transmitting a single broad beam at near normal incidence to the seafloor, and then it uses the spatial and temporal coherence of seafloor scattering, correlating the signals across an array of hydrophones, and it estimates velocity from those correlation coefficients. Near normal incidence, that's where the scattering strength of marine sediments is generally the greatest, and a single broad beam lets you work at a lower operating frequency. All of that's favorable geometry for low power. So this is kind of the approach we started pursuing to see if we could make this work in a really tight space. A CVL works based on what they call in the literature the principle of waveform invariance, and it's kind of a confusing name. All it says is that 2 signals are coherent or the same if they share a common midpoint between the point it was transmitted from and the point it was received from. So in this really simple example, we've got a projector and 2 hydrophones separated by a distance d. Their midpoint we'll call the phase centers, and those are the unshaded boxes in the middle. And at some time later, the arrays moved forward to where it's now shown in green. And you can see we have overlapping phase centers, or 2 common midpoints. And here I'm just getting rid of everything that doesn't correspond to those midpoints. So you can see the projector in hydrophone 1 at time 1 shares a midpoint with that same projector, just moved forward a little bit, in hydrophone 2 at time 2. We find the distance it had to move to reach this condition is half the separation between our hydrophones. We'll call the time it took to get there tau. And from that, you can get an equation for your velocity. If we want to do this in practice, it's a little bit more complicated because things don't always line up perfectly like that. So let's look at a more complicated example here. We've got a projector on the right and 4 hydrophones in black. Their phase centers are the circles in the middle. And the phase centers are all a distance delta apart. By the time we've received the second ping, the arrays move forward. I've gotten rid of everything, just, so we're looking at phase centers now. And we moved forward a distance so a little bit more than 1.5 phase center spacings, or between 1 and 2. So if we make a plot where on the x-axis are all the possible phase center separations, all the points are just going to be at integer multiples of delta, because that's the spacing of the elements in our phase center array. On the y-axis, we're going to plot the correlation coefficient between the signals on ping 1 and the signals on ping 2. When you look at this plot, you'll see we don't have any correlation coefficients of 1 because we don't have any phase centers that are in the same place. We do have some points that are reasonably highly correlated though, and those correspond to the nearest neighbors. We moved 1.5 delta, we have points at 1 and 2 delta that are pretty highly correlated. So to refine our velocity estimate, we could fit a curve through this data. The peak of that curve is going to pretty closely correspond to our actual advance per ping. Now, a property with a property of the correlation coefficient is that it's really only the high value points that are of any meaning to you, because the low value points have a lot of statistical estimation error. They've got a lot of variability and they have bias in them, so you can't really trust what they're telling you. So we need more green points to get a better velocity estimate. The way we can do that, add more channels to our array that more finely samples this curve. We get more points in the green to work with. But if we're moving a little bit faster, we go a little bit further between our 2 pings. And now we have to grow the extent of our array in order to have overlapping phase centers again, or partially overlapping phase centers again. So you're seeing this drive towards finely spaced samples, large spatial extent. Large, densely packed arrays do not exactly scream, fits on a small vehicle and is low cost. So we'll get there in a second. The other way we can improve the number of points we have in the green is get more information, and we do that by transmitting with more bandwidth. More bandwidth is more information acoustically coming back in our returns. So to make this thing small and low power, we had to rethink the way a CVL could operate. And this kind of led us back to understanding some of the fundamentals of coherence of seafloor scattering. The way our CVL works is we transmit an ensemble of pulses into the water. Here I'm drawing just 4. In practice, it's many tens or hundreds. And we're going to look at a 2D array here. It's 6 elements spaced around in a circle. I'm just drawing phase centers again here, the midpoints between the projector and the receiver, the things that we actually need to overlap. And as we receive each echo, our phase center array is moving along with the vehicle in space. And by the time we've received all of these echoes, if we correlate every signal against every other signal, we'll find some reasonably highly correlated points because we had some elements, some phase centers that were near each other in space. To get some velocity information about this, we have to do a pretty complex fit to the data. We have to fit a function to it that's the shape of it is based on the shape of the spatial coherence function for seafloor scattering. So that's an aspect that we had to go back and study some more to make this thing accurate. The data that's going in there is a function of space. And in this array, the spacing between our elements on different pings, it's not known to us to start because it depends on our velocity, and that's what we're fundamentally trying to figure out. But we do know the starting geometry of the array, that's x naught in this equation. We know the time between the pulses that we transmitted because we did that, we put them out in the water. And then that just depends on the velocity. If we assume the velocity is average over this period, we can solve this equation, and what comes out is an estimate of our velocity, and we can get that in 3 dimensions, just from this simple array. To demonstrate this, we built up a prototype. So it's made out of piezoelectric hydrophones. PZT4 is the formulation we use. Excuse me, the projector's on the left there. It's about the size of a quarter. It transmits at 300 kilohertz. It's coupled into the water through a matching layer made out of PVDF. That just helps us get more bandwidth out of it. The hydrophones are also made of piezo ceramic discs, and they're arranged in this geometry that we'll see again in a second. That just gave us a lot of different configurations to help understand performance trade-offs when we looked at this experimentally. It's all set on a block of syntactic foam. This is a lead-loaded syntactic foam, so it's really lossy to acoustic signals, meaning that signals coming in and out of the back of the array are attenuated, so we're really only seeing signals between the front of the array and the bottom of the seafloor. And then it's all set on top of a watertight box that has the electronics in it. We tested this out at Seneca Lake, so this is work I was doing when I was still at Penn State. Seneca Lake is great because it's a freshwater environment. On the middle of the lake, it's about 180 meters deep. So you can get some, reasonably good experimentation done, especially when you're in central Pennsylvania and getting to the coast isn't as easy as it is here. We strapped the array to a pontoon boat, tested out at a variety of different depths, velocities. The track I'm going to show you is this one here in orange. We were in 60 to 65 meters of water. We're putting 40 pulses into the water, about 2 milliseconds apart. Our array geometry gave us a lot of configurations to look at. We're going to look at 2 subarrays here, the elements in blue and the elements in red. We had a ground truth velocity estimate from a fiber optic gyroscope and inertial measurement unit. It was aided with GPS and RTK correction, so we had a really high quality reference to compare to. And then we form velocity estimates from our array to compare to that. I'm separating them into the forward and a thwartship component, so you can see at the start of the track, the vehicle's ramping up and eventually plateaus around 1.6 meters per second. There is some athwartship velocity, but I mean, come on, it's a pontoon boat. It's pretty much only going straight. So the little bit of athwartship velocity we're able to track as well. We do see that our velocity estimates are biased. We're estimating a little bit more velocity in the forward direction than there actually was. And what that comes down to is a few reasons, but it's mostly how we're sampling the spatial coherence of the scattered field, how accurately we're able to tell how similar 2 measurements are and understand what that complex function really looks like. I'm going to move on and talk about imaging.
I have one question.
Yeah.
You said you compared it against a unit that had inertial measurement.
Yep.
and GPS, but if you're at 65 meters, how are you getting the GPS signal?
We're on the surface.
Oh, you're on the surface, sorry.
Yep.
Okay.
Good question. We'll talk about imaging next. And what I'm using Coherence for is for imaging for UXO remediation. This is a very real problem that we're trying to solve today. So this map here is of the Chesapeake Bay in Maryland near the Patuxent River Naval Air Station. So the Naval Air Station's been used for military training for many decades. As a result of those activities, munitions have ended up in the water. Through sediment transport and currents, they can migrate. They can start on the surface and they can bury, they can come back up. And they're believed to have, over time, started moving south to where they're now, where there's residential development going on. So a nice subdivision, waterfront property, but the potential for human contact with UXO, unacceptable. So we need to figure out how to find them so that they can be remediated. This is work that's been supported by CERTIP, the Strategic Environmental Research and Development Program. They've kind of taken the charge in the US for figuring out how to solve this problem. The platform we're using is called the Sediment Volume Search Sonar. This is something we started when I was at Penn State. It's a synthetic aperture sonar mounted on the forward section of a pontoon boat, so nice shallow draft. We can get into these very shallow areas. The array's on the forward section on an array plate. We keep it up out of the water for transit and then can drop it down below the depth of our pontoons when we're ready for survey. And this is a pretty complicated sonar. So it's a synthetic aperture sonar with 5 projectors. They're in blue along the back of the array. They transmit in sequence from port to starboard, 1, 2, 3, 4, 5, and again, 1, 2, 3, 4, 5, all as the vehicle's moving in the forward direction. The signals go out, they scatter off anything that's down there as well as scatter off the environment, and they're received by an array of 80 hydrophones. They're shown in yellow here. We can take, we'll look at this one. This is just an illustration of kind of what's going on here. So the array is about 1 meter off the seafloor. You can see the sediment water interface there, and we're transmitting sound down at near normal incidence to the bottom. It's interacting with the bottom and then penetrating into the sub-bottom so that we can interrogate targets that might have buried as well. Sound scatters back to us, it's received on the hydrophones. And this is an example of the imagery we can make. So it's a 3-dimensional image product. The red direction, we'll call that the along track direction. That's the direction the boat was primarily driving in. Green is cross track or a thwart ship. And then blue is depth, going down from the array plate into the bottom. And you can see we went over a few targets here. These are man-made objects. In particular, you can see a big solid cylinder in the middle of the image cube there. Below it, you see this ghosting effect. And what that is elastic ringing. So these man-made objects, especially ones that are science targets, spheres and cylinders that we put down there, if you tapped on them, they'd want to ring like a bell. And so when you couple sound onto them, they start to resonate as well. And that stored energy re-radiates later in time and shows up as this unfocused energy below the depth of the target. When we do this in a field test, this is on a target field that we installed, so we had objects that we know what they are and we know where they are. We often see that the outline of the target doesn't show up great in the imagery because it's competing for contrast with scattering from the sediment. You can see the elastic scattering below. It tells you there's probably something man-made there, but we're not sure if that's really a reliable feature for a couple reasons. These are like exceptionally smooth objects that we've put down in our target field. Real UXO, after it's spent some time underwater, might not ring all that well. It also tells you that it's probably a man-made object, but it doesn't tell you what it is. That could just as well be a scuba tank. And when you're in the UXO remediation business, sending trained divers down there to find something and dig it up safely is really expensive. So you want to be digging up, things that are probable, not just all the trash that we left down there. So the seafloor is strong, but the signals that come back are diffuse. They're kind of random in nature because so is the seafloor. And that's what we're trying to exploit to see if we can resolve these targets a little bit better. Conventional sonar imaging is not that complicated of an algorithm. It's just delay in some beamforming. So in this simple example, we've got a transmitter T, it's sending a pulse out into the water, it's interacting with the environment, the little red object there, anything that's there, it's scattering sound back and it's being received by all the hydrophones. If we wanted to form an image and figure out the value at that pixel, that black square there, the delay in some beamforming algorithm just says you take the signals you recorded by your hydrophone, so that's pressure is a function of time. The value at that pixel, you first calculate the delay. So you calculate the round trip propagation time from when sound was transmitted till it got to the center of that pixel and back to a hydrophone. You go into your time series and you grab the value of the signal at that time. So that's the delay. You then do that for all of your channels. You grab all of those different values at all their particular delays and you add them up. That's the sum. So you just made one pixel in an image, you've just got 10,000 more to go, and it's all done. So it's making an image of the reflectivity of the scene or the scattering strength. But there's more information there in the acoustic field that we're not leveraging. And that's what we're trying to do, to use the coherence of the field to improve this image. The reason we think this can work is because the biomedical acoustics folks have been doing this too. In biomedical ultrasound imaging, there's been a few different ideas that have explored this. I'm showing two of them here. On the top is imaging a human carotid artery. On the bottom is an image of the human heart with ultrasound. The left side is all the data reconstructed with standard conventional delay in some beamforming. On the right is imaging with spatial coherence-based reconstruction. And there's a few different flavors of algorithms. These are two different algorithms shown in an example here, but they're essentially trying to do the same thing, use more information and make a better image. And you can see they're successful. The contrast in the imagery is definitely better. You can see the objects a little more clearly, the speckles reduced, and in some cases the resolution is better. It's also, not like, oh wow, it's amazing now, but when you're trying to find really hard objects to see, every little bit helps. What they're all trying to exploit is that the scattering from a target is going to be more coherent than scattering from the background. So in this example, it's a very simplified ultrasound array. It's got 8 elements. They transmit sound out of the middle 4 elements, and they receive it on all the channels. If you made a plot, on the x-axis is the spatial lag, or the spatial separation between elements. If you looked at a point reflector, something that scatters sound equally in all directions, you'd see that the correlation between the signals on all the elements, it's always 1. They're all seeing exactly the same signal. So you get that nice big red line at 1 for all spatial lags. When you're looking at the background's composed of rough random inhomogeneities. I guess in this case it's human tissue. It's not necessarily rough, but it is random. That diffuse scattering has finite spatial coherence, and what that means is elements in the array that are really close to each other, so elements 1 and 2, for example, they're going to have signals that are pretty highly correlated. But as you get further out across the array, the correlation is going to start to go down. And this is what we're trying to exploit. Targets have high correlation in their signals across the array. The background does not. So you can look at this in simulation. This is a simulation I put together. It's a sonar array flying over a simulated scene. It's got a few things in it. We're going to look at a cinder block that's it's partially buried into the sediment, and a model of a munition, a howitzer shell, also partially buried near the surface. We form a 3-dimensional image product. So we're going to look at this first in a cross-track slice. So taking our 3D matrix, just taking a slice down the middle of it, and that slice is going through the middle of where we expect that howitzer shells to be. We're then going to take a slice in an orthogonal direction, taking a slice through depth. So taking a slice near the surface of the object, and that lets us see approximately the 2 targets at the same time. On the left, that's imaging with conventional delay in some beamforming. On the right, this is just taking the basic algorithm used in some of the biomedical literature and reproducing it on sonar data. And what this tells us is we're seeing promise. I want to point out a few things. So we can see the features of the cinder block a lot better. We can see the indentation in that. When you're trying to, again, image really hard to find things, this little bit of information helps, especially as we start to give these imagery to machine learning algorithms. For the munition, we can also see the shape of the taper on the nose cone a lot better. When you're trying to identify which munition is it, again, this little bit of information can help tell you that. And again, we've got the speckle reduced, so the contrast of the object versus the background's a lot better. Now, a simulation's only as good as the model underneath it, so I also like to start looking at things with experimental data. Something I do a lot in my work is with in-air sonar. So working in air lets you get experimental data that's not tied to the accuracy of some model, but it's so much cheaper than working underwater. It's also a lot easier to work in air than it is underwater. And so when you're trying a new high risk, hopefully high reward idea, starting in air is a place to check inexpensively if you're on the right track. So in this example, I've got an array. It's got a speaker and 4 microphones. It's on a linear actuator that's 5 meters long. It's in a room roughly this size. So the array moves down the length of the actuator, pinging at regular intervals as it goes. And this lets me install targets in front of it that I can observe and know what's down there. I filled up a sandbox basically with plastic beads. These plastic beads scatter sound randomly and diffusely with properties similar to like what we'd see for scattering off the seafloor. I then just machined a bunch of targets. Here I made block letters, the letter Q. They're about 8 inches in diameter. And I took them and I just partially buried them into my ensemble of plastic beads. Reconstructing this, on the left is conventional reconstruction, regular delay and some beam forming. On the right is using the spatial coherence of the field in the reconstruction. And we see promise like we did in the simulation. The contrast against the background's a lot better. We start to see the resolution, especially for some of these finer features around the intersection of the leg of the Q with the body. We see that come out clearer, and we think this is on the right track. So what we're currently investigating is, right now we're just taking biomedical algorithms and applying them to sonar data. And we're trying now to fine-tune those algorithms for the particulars of sonar imaging. A sonar array is, similar to, but not the same as a medical array. So a sonar array, particularly a synthetic aperture one, it moves through the water, and it has to move through the water for us to form that image. So there's necessarily motion involved. A medical array, it's fixed on a probe. Unless you move the probe, the array doesn't have to move. Sonar arrays tend to be undersampled as well. Medical arrays are critically sampled. So that's a big difference in how we sample the acoustic field that we think is about to matter. There's a major difference in how sound interacts with the environment as well. In medical ultrasound, through some gel, the probe's directly coupled into human tissue. So you're just measuring scattering off of the volume of tissue. Underwater, when we're imaging into the sediment, we have scattering from the sediment-water interface as well as from the sediment volume. And at any point in time, those two things can arrive simultaneously. So there's always a contribution from the interface, even when you're trying to look down deep. That matters when you start to think about spatial coherence, as does the geoacoustic properties of the seafloor. So the seafloor doesn't scatter equally in all directions. Some angles tend to scatter sound more favorably than others. That distribution of energy is a distribution of energy in space, so of course that's going to affect the spatial coherence, as does how much the sound is attenuated as it propagates into the bottom. We think by using some of this information in the biomedical type algorithms, we're going to make the imagery even better. We're going to get to the final topic here now on monitoring. And I want to look back to using the in-air experimentation. So we've got our bed of plastic beads. There's no targets here, it's just plastic beads, all rough and random out there. I ran the array down the track and I formed an image. And the image is just speckled because it's just rough information coming back, random signals. And then I did it again. But before I did it again, I thought it was a good time to practice my Zen gardening. I don't get enough time to do that these days. So I grabbed a broom and I just gently perturbed the top of some of the plastic beads. Not enough to form a divot, just kind of moving the plastic pellets around. And I formed an image that looked almost exactly the same. Because this is an image of the scattering strength of the seafloor. Moving around a few plastic beads doesn't really change the roughness. The signals that come back are the same strength. But moving a plastic bead does change the phase of the signal because something was a little bit further away and it came back at a little different point in time. So if you take these signals and go point by point, computing the correlation coefficient for them, you can see what I put into the beads. So the points that are in blue are low coherence. That means something changed. The points that are in white are high coherence, and that means nothing changed. You can see how we can start to use coherence to tell when something changed and where it changed. So the geometry we're going to think about for doing this with the seabed is an array that's sitting, I'm sorry, it's not an array, it's just a single echo sounder. It's sitting a few meters above the seafloor, looking out at shallow grazing angles. It's tipped down about 15, 20 degrees, pinging the seafloor. When you ping the seafloor, the signals that come back are pressure is a function of time. And time through the sound speed is really just encoding range from the echo sounder. You see the signals rise up. They get very loud as we first have sound interacting with the seabed. Then they gradually taper off as we're scattering off things that are further and further away from us. The signals, though, are just a function of what's down in front of the echo sounder. So if we ping again immediately later, we're going to get the same signal back because the environment's not changing, so why should the acoustic signal? But the seafloor does change, and if we wait long enough, we'll see the signal that comes back change. It's not really any louder or quieter, but the signal looks different. The places where there's peaks and there's zero crossings are no longer the same, and so we can capture that with correlation. There's a lot of reasons the seabed can change, though, and this has been studied some, but it's mostly been in shallow, sandy sites. We're interested in the broader picture of the ocean. You know, it's deeper than 40 meters and almost everywhere. It's mud, it's silt, it's rock in different places. And this, the differences in physical scale and complexity are going to manifest in how quickly things change and at what rates they change. Things can happen on multiple timescales. It could be tidal, it could be seasonal, it could be storm driven, but the seabed's also home to a lot of organisms. Organic activity, biological activity down in the seabed is going to naturally change the bottom as well. And so we expect to be able to see all of this change over time with coherence. This is a project that I've been working with collaborators at UNH here. Tony Lyons, Gabe Venegas, and Jenna Hare have all been really helpful in seeing this through. So we built a custom instrumentation platform. This is a quad pod lander. It's an aluminum frame that houses all of our instruments, and it's set on top of an anchor. We build it up at the pier, we fork it over, and it's craned down onto the UNH Gulf Challenger. It has a bunch of instrumentation on it. So for acoustics, we care about the echo sounders. We've got echo sounders at 3 frequencies from 38, 70, and 200 kilohertz. Different frequency is a different wavelength. Different wavelengths means we're going to be sensitive to changes at different spatial scales. We also expect those different spatial scales will have different temporal scales. So this helps us tease apart the multiple different things that might be going on the seafloor. To help us understand the environment a little bit better, we have a CTD that tells us something about the water properties. It also has a dissolved oxygen sensor. That gives us some information about what the biology might be doing. We have an ADCP looking up into the water column, giving us information about the local currents. We also have a set of cameras. We have forward-looking cameras and lights. That tells us what the echo sounders are scattering off of. We also have downward-looking cameras and lights in a stereo pair. That's going to let us do photogrammetry of the seabed that's directly below us and get some non-acoustic measure of how the seabed's changing as well. So this gets deployed, it sits down on the bottom. When we're ready to recover it, we have a pair of acoustic releases. We communicate with them, they drop the anchor and the buoyancy brings it back to the surface so we can recover it. We also have a recovery beacon built in case something goes not as planned and it comes up early, or it comes up and we can't find it. That'll get a GPS fix, transmit it to us over Iridium, and we can go find the lander to recover all our instruments and our data. So we deployed this in Wilkinson Basin off the RV Gulf Challenger just a few weeks ago. Concave came out with this. He was gracious enough to help and also captured this drone footage. So we're about 60 kilometers offshore in 160 meters of water. And we're gonna drop the lander down to the seafloor. Here we're just preparing the rigging to get it ready to go. And when we lower it down to the bottom, it is capable of free fall. In this case, we wanted a little bit more precise control over it. So we're gonna winch it all the way down until it's about 5 meters off the bottom. So we drop it off the side, and we have a third acoustic release in the rigging in line there. And so we're gonna lower it slowly. It takes some time to get down there. And when it's about 5 meters above the seafloor, we're gonna talk to that third acoustic release there in yellow, and we're gonna drop it, and it's gonna sit on the bottom. So we did a test in shallow water just to make sure everything was working as planned. And so this is imagery captured from our cameras then, just to give you a sense of what we're trying to do and what it might look like. So as we drop towards the bottom, the seabed comes into the view. We sit down on the bottom, of course, churn up all kinds of sediment that we have to wait for that to settle out. That took plenty of time, but eventually it does. And so on an hourly basis, we're just going to interrogate the seabed, and we're going to do this for 9 months, collecting data about the exact same spot on the seafloor again and again to use coherence. Until we recover it, we drop our anchor, and we float back up to the surface so we can get the vessel, get the data from the vessel. So we don't have any results for 9 months, but hopefully a year from now, we're here sharing you everything interesting we found. So I'm going to wrap up now. We talked about using coherence for a lot of things. It's just the similarity of 2 signals, but it can help us navigate. We talked about how to use that on an unmanned vehicle, designing a custom array. We then talked about how to use it for imaging. The biomedical ultrasound communities found ways to exploit the coherence of signals to make a much better image. We think we can do this underwater too, to better find UXO where it might come into human contact. We use some in-air experimentation to test out our ideas, and then we use that in-air experimentation to motivate this idea that we can see change through coherence. We've got an experiment running out in Wilkinson Bay for the next 9 months. We deployed it off the Gulf Challenger with all our equipment. It's looking at the same spot at the seabed, hopefully about to tell us what happened, why, and how it got there. And that's it. Thank you. Yeah.
For your UXO research, what simulation were you using to replicate that for your box?
Yeah, so that's a model. It's called the point-based sonar signal model. It's something we developed at Penn State. It's essentially a model of models. So it's using a model to describe scattering off the sediment-water interface. It's using another model to describe scattering off the sediment volume, and a third model to describe scattering from the target.
Okay.
Yeah.
Any other questions?
Yeah.
Yeah, I have a question. That was really nice. Thank you for giving that presentation. The complexity of the heterogeneous seafloor,
Yeah.
how much heartache does that give you? I mean, you've got the camera there looking at the bottom. Does that help you understand what you're seeing over time?
It does. So, the heterogeneous seafloors are obviously challenging, but that's also why they're interesting. And that's the type of seafloor that's been less understood in the acoustics world for sure. I guess we don't know what to expect. I hypothesize that you're gonna see shell hash and things like that move around differently than maybe biologic activity in the silt below it. So we don't exactly know how that manifests in the acoustic signals yet, but we also know we don't have enough data to even begin to model it. So this is an experimentation to figure out what we don't know as much as how to figure it out. Yeah.
Back with the UXO piece, how long from start to finish would it take to deploy the unit, start the scan, and then post-process all the data of like a medium-sized board, I guess?
A day.
A day?
Yeah, and really the obstacle is survey time. When you're looking down, you're making a track that's this wide. So if you want to cover every area and cover it accurately, you're mowing the lawn in a really tight pattern. The reconstruction's actually faster than real time, so that's not an obstacle.
Okay, interesting.
Maybe the other obstacle is we haven't solved the how do you figure out what's their problem. So you can't yet give this to machine learning algorithms and have them work successfully. So right now, some poor person has to look through this and click on everything they think that might be a bomb.
Yeah.
So you mentioned it's going to be on the seafloor for say 9 months, are you concerned about like barnacles growing on the cameras or like sort of biology interacting and giving error?
Yep.
To just, yep. Like, I guess, what are your thoughts?
We have some experience. Jen Mixes-Olds has had landers quite near this site, and her experience has been that the biofouling isn't all that bad. She goes out for with her landers for a year at a time. You can put biofouling coatings on. We thought about putting that on our transducers. You know, barnacles and stuff growing in front of where you're transmitting and receiving sound absolutely changes what you see. It's really hard to quantify. Putting on a coating that degrades over time also changes what you're expecting to see. So no one solved this problem. It's something we're thinking about though. Andy.
Are you in a no fishing zone or?
We are. Yeah, so we're in a year-round no ground fishing zone. So we expect it's just gonna sit there. We hope. Sylvan, yeah.
I was wondering, you're talking about having to go through and select everything, and I'm assuming that data is fed into machine learning algorithms, so that's sort of a future answer to the question. But I was gonna ask is what kind of techniques can be used to or if there are techniques that are used frequently to sort of try to have some confidence in where there might be an interesting features. You don't have to go through like 9 months of data, like maybe like say like, oh, these few frames have some anomaly. Is that
So are you talking about our lander or with the UXO? Or all of it?
I guess all of it, but I mean, but specifically in terms of scanning in long tracks of data where the machine learning can't quite identify things. If there are techniques that you know of or use or know people that use that can narrow down time periods or locations where there might be something more interesting, like looking at correlation or whatever.
Yeah, it's a great question. This is an active area of research that I don't work in, but I work with people who do. You know, they break the problem up into two parts. So there's a detection problem of is there something there, you know, in this chunk of time or in this chunk of space? And then if there's something there, what is it? And that's the classification problem. So the detection problem, it's a little bit further along. You know, it's essentially looking for anomalies above the background. And so if you can kind of figure out what the background is, there's more background than there are anomalies. You can generally start to find detections. The classification, it's an open problem, and we don't have an answer right now.
Sorry, could I?
Yeah, go ahead.
Quick follow-up. In terms of like detection, like what kind of like statistical measures are used to try to isolate times with the detection?
Yeah, it depends on the thing you're looking for. We should chat about this more offline because it gets really deep into statistics of seafloor scattering. And the particular distribution that you use has a big impact on how accurate you're going to be. Yeah.
Without a tether connected to the system, how do you run power to the camera for 9 months?
It's all batteries. So most of these black canisters sitting there, that's our battery power. Right?
Yeah, I was just on the pontoon boat, the
Yeah.
receiver array, I was just curious there seems like there's a rhyme and a reason to all the things you're doing. Why is it shaped the way it's shaped? Why isn't it a regular?
Yeah, mechanics that the physical supports that we need to latch onto to drop the array kind of narrow into our moon pool there, and so we had to tuck the array in. Now, in reality, for most of the imaging that we've been doing, we only use the back two channels of hydrophones anyway. So that's 16 elements that we really use out of 80. So the rest of the 80 don't get a lot of use.
Just kind of oversnapping.
Exactly. Yep. Yeah.
Yeah, very good presentation. I know you said when you started the presentation that you were using correlation and covariance to kind of compare the two signals, like which you said covariance is probably better. Like I was just thinking, are there other statistical measures that one can also use for this kind of comparing two signals?
I'm sure there are, I'm not a mathematician, so these two dumb comparisons are, all I know how to use. That right now it's working out, but I probably should talk to someone who knows more. There might be some better ones.
Okay, thank you.
Sure. Other questions? Yeah.
Is your velocity estimation uncertainty equal in all dimensions, do you think? Or is it more sensitive to horizontal or?
It is definitely not equal in the forward and athwartship directions. Sorry, those likely are the same. It is not the same in the out of plane velocity. This is a research question we're still trying to study, is we don't have an error model for this sensor yet. I don't know the answer, but I suspect it is not the same in all directions.
If I could ask a follow-up question.
Yeah.
The geometry of the array for that was interesting to me. What was sort of the thinking in that sort of octagonal shape?
Yeah, so it's essentially sampling a circle, and our thought was these small vehicles are not strong enough basically to swim, in a straight line. So they're gonna have a ton of crab. So our velocity very well could be sideways at some times, or, if we're not strong enough, we could be going backwards. So we felt like we needed a sensor that could be accurate in all directions. Yeah.
Just another question, sort of thinking about the site that you chose.
Yep.
Do you have an anticipation for I guess the oceanography of the area, how frequently the seafloor is gonna change from video to video to video sample?
No.
Just be surprised.
And I think, change, it's a broad question, right? Because it's got multiple scales of change. In the sense that I bet it's still silt when we come back a year from now. It didn't change. But in terms of, the roughness, I think it could change on the order of hours. Tom?
Do you expect that change to arise from biological activity? Because it looks like there's a lot of shell hash there, or would you, I thought Doug had some current profilers out there. Do you have an idea that the flow is strong enough to move sediments?
Our hypothesis is out there, it's gonna be primarily biologic activity that's driving it. The shell hash we, saw, that's in shallow water,
Oh, that was the shallow.
yeah, that's 10 meters from the pier in case something went wrong. So we don't think there's gonna be that much shell hash out there, but in shallow water, at other sites, generally people have seen that it's storm activity that can be the biggest driver. Our hypothesis is in deeper water, it's gonna take a really big storm to churn up the bottom in the same way, so it's probably gonna be biology that drives it. But
60 meters, was that, what was it?
160.
160. Are they lobstering out there? I don't know how far they go for that.
We don't believe they are. Yeah.
I might have missed something, but I'm just curious, on the video of your lander.
Yep.
You had some footage of what it looked like while you were still connected in the bottom. And then you tripped the release and then it went up. But you don't have anything, you're not transmitting anything to the surface, there's no buoy cable going up there. How did you get that video? Or was that a previous?
That was our test deployment.
Test deployment, okay, that's what I figured, yeah.
So hopefully it looks like that in 9 months too. Yeah.
Yeah, so I actually have a follow-up question
Sure.
on that. So when you go through all that data in 9 months from now, are you planning on just having a team of people to actually look through it by person, or are you going to try to implement machine learning or?
We're gonna start with just physics-based analysis of the data. And so there's 4 of us on the project, there may be more in a year. All kind of trying to answer different questions with this data. I'm interested in coherence, Jen is interested in scattering strength. We're both looking at the same data, hopefully both finding the things that we each have to pay attention to. But it's a good question. Val?
You mentioned that I want to get this wrong. There's a lot of spatial not coherence, like whatever you call not coherent.
Incoherent?
Incoherent, thank you. Like as you move along this synthetic or real array from a point on the seafloor, seafloor? And that's just the geometry of the return, is that right? Because the scattering is not isotropic in all directions?
It is related to that the scattering is not isotropic. Really down in the weeds of the math, it's related to the angular spectrum of the signals. So that's a function of how the seafloor scatters versus angle, but also how you put sound out as a function of angle. So it's tied to the seafloor as to your array's property.
So my follow-up question, and I don't know if this makes any sense, but can you separate the returns from the seawater, seafloor interface from the volume returns using that difference?
I think you can. I have that as an open item I'm trying to tackle.
Cool. Yeah,
Need a few more hours in the day. Any others? Good deal. Thank you very much.